6,000 worlds, and not a single photo resembling Earth. This isn't an exaggeration or a figure of speech. To date, astronomers have confirmed the existence of more than 6,000 planets beyond our solar system. That's more than the number of stars you can spot with the naked eye on a clear night. And the list keeps growing every month. New names, new orbits, new masses. Yet among all the planets humanity has ever observed directly, in visible light, infrared, or any other way, not one looks like Earth. Not a single super-Earth. Not even one that vaguely resembles Neptune. It's as if we compiled a phone book for an entire city without ever seeing a single resident's face. And here's where we need to pause. If we've discovered 6,000 planets but barely photographed any, then how do we actually know they exist at all?
And here it is.
The answer sounds almost absurd. The vast majority of exoplanets are discovered blindly, not through a lens, not in a photo, but through a shadow, through a subtle tremble, a barely noticeable flicker of a distant star. The transit method works like this. A planet passes between us and its star. The star's brightness dips, just a fraction of a percent. A telescope catches that dip, and by analyzing its depth and timing, astronomers figure out the planet's size and how far it is from the star. Simply put, we don't see the planet itself. We see its shadow cast on a distant light. The second tool is the radial velocity method. The planet's gravity tugs on its star. The star wobbles slightly. This wobble shifts the star's light spectrum, sometimes toward the red, sometimes toward the blue. The shift is tiny but measurable. From it, scientists calculate the mass of the unseen planet. There's also microlensing, when the gravity of a distant star and its planet bends the light of an even more distant source. But this is pure rarity, a one-time stroke of luck. The effect lasts only days or weeks, then never repeats. All three methods share one thing. None of them produce an image, no pixels, not even a speck. We know the planet is there. We know its mass, its radius, its orbit. But what it looks like? No idea. And this is where the real mystery begins. Because direct observation, when a telescope actually captures photons reflected or emitted by the planet itself, does exist. Yet the results from this method are more baffling than triumphant. According to various catalogs, astronomers have directly observed between 61 and about 100 exoplanets, out of more than 6,000 discovered. That's less than 1.5%. Imagine looking at a world map from a satellite and only being able to spot Monaco and a few neighboring villages. But here's what's both fascinating and troubling. Every single exoplanet ever captured in a direct photograph turned out to be a gas giant. Blazing, massive spheres made of hydrogen and helium, weighing several times more than Jupiter. No rocky worlds, no oceans, no atmospheres where, in theory, rain could fall as water instead of molten iron. And they don't orbit where we expect to find life. Most of the planets we observe directly lie at enormous distances from their stars, tens, hundreds, sometimes even thousands of astronomical units away. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. These giants hang so far from their stars that Pluto, by comparison, feels like a close suburb. They aren't cold, at least not all of them. The younger ones still blaze with leftover heat from their formation. That's exactly why we can spot them at all. They glow in the infrared spectrum with their own residual warmth. The picture is strange. We can only see directly what looks least like Earth. Enormous, scorching worlds far beyond the zone where water could stay liquid. Meanwhile, the things we truly want to find, small, rocky planets at just the right distance from quiet stars, remain completely hidden. We know these planets exist. Transits and radial velocity measurements shout their presence. But no telescope has ever caught a single photon directly from them. The issue isn't how hard we try. The problem lies in the star's own light, which makes this task physically brutal, so much so that even the nearest potentially habitable planet, just 4 light-years away, looks like a faint, invisible dot next to a dazzling spotlight to our best instruments? The answer lies in brightness contrast. A typical rocky planet, Earth-like in nature, doesn't generate its own light. It's cold, it's dark. All it can do is reflect a tiny fraction of its star's radiation back toward us. And that fraction is minuscule. The brightness difference between the star and such a planet is about 10 billion times. 10 billion. This isn't just a number. It's a gulf too vast for any existing instrument to bridge. Young gas giants tell a different story. They still burn hot from their formation, their cores holding on to leftover heat from their birth. That heat seeps out as infrared radiation. In fact, they glow on their own, not by reflecting light, but through their own emission. That's why astronomers have managed to photograph a handful of these giants. The brightness difference between them and their star drops to just a few million times. But that's the exception. These giants are swollen, scorching, and useless when it comes to hunting for life. Meanwhile, a rocky planet in the habitable zone, a small, cold world, reflects 10 billion times less light than its star does. Put simply, we're trying to spot a dark speck right next to a blazing campfire. And here's where the second problem kicks in, making the first one impossible to overcome. The distance to the stars is staggering, but from the perspective of an observer on Earth, the real challenge isn't how far a planet is from us, it's how close it is to its own star. When viewed from several light years away, the planet and its star blur into almost a single point. The angular distance between them, that tiny gap a telescope needs to resolve to separate two objects instead of one, is microscopic. Take the main clue, Proxima Centauri b, the closest potentially habitable exoplanet to us, just over 4 light years away. On a cosmic scale, it's like living next door. If there's any object we should have photographed first, it's this one. Yet it remains unseen. Not a single telescope has ever captured it. Not once. The angular distance between Proxima Centauri b and its star ranges from 39 to 65 thousandths of an arcsecond. To grasp how tiny that is, a full circle has 360 degrees. 1 degree breaks down into 60 arc minutes. Each arc minute splits into 60 arc seconds. And an arc second's thousandth part is an arc millisecond. We're talking about a gap 20,000 times smaller than the moon's apparent diameter in the sky. Imagine a penny lying on a sidewalk in New York City. You'd have to look at it all the way from Philadelphia to see it. And right next to that penny shines a spotlight 10 billion times brighter. That's the catch. The problem isn't one-dimensional. It has 2 layers, each manageable on its own. But together, they form a wall. The first challenge is contrast. The planet is just too dim. The second problem is angular separation. The planet sits too close to its star in the sky. If the planet were dim, but far enough from the star in angular terms, you could simply point a telescope slightly aside and catch its faint signal. If the planet were bright but close to the star, you might still be able to isolate it from the star's glare. But here's the catch. It's both dim and squeezed right up against a blinding light source. It's like trying to spot a moth fluttering around a stadium spotlight. Not from inside the stadium. Imagine watching from hundreds of miles away. That moth reflects the spotlight's glow, but 10 billion times weaker. And it never strays more than a couple of centimeters from the lamp, at least as far as your eye can tell from that distance. But the spotlight's light doesn't behave like a neat, sharp point. It spreads out. No matter how advanced a telescope is, it turns a pinpoint star into a blurry smear. And that smear covers the very spot where the planet hides. This is where the challenge shifts from difficult to seemingly impossible. It's no longer about the sensitivity of the detector or the size of the mirror. The light itself, passing through the lens, follows physical laws that blur it across the sensor. And everything we're trying to detect gets lost in that blurred halo. The first thought that comes to mind? This must be an optical flaw. Lenses aren't perfect. Mirrors get polished with tiny errors. The whole setup vibrates. Fix the flaws and you get a sharp point. Makes sense. But it's completely wrong. Light is a wave. Not metaphorically, not in some abstract way. It's literally a wave, with peaks and valleys, about 500 nanometers long for green light. When this wave passes through a round opening, like the pupil of your eye, a camera lens, or the main mirror of a telescope, it bends around the edges. It curls inward, interfering with itself. This effect is called diffraction, and you can't get rid of it. Not because engineers aren't trying hard enough, but because these are the fundamental laws that light follows. Because light behaves like a wave, a telescope with a circular aperture doesn't focus light from a pinpoint source into a single point. Instead, it forms a diffraction pattern, a bright central spot surrounded by a series of concentric rings that fade toward the edges. In 1835, British astronomer George Bedell Airy described this pattern. Since then, it's been known as the Airy disk. Put simply, even a perfect telescope with a flawless mirror operating in a vacuum under total stability can never focus a star down to a single point. The point itself is impossible. Only a spot is allowed. And that's where the real problem begins. At first glance, a spot is just a spot. Small, neat, right in the center. What could be so troubling about it? But the size of this spot sets what's called the diffraction limit of resolution, the fundamental ceiling on sharpness for any optical system. The bigger the Airy disk, the harder the telescope finds it to tell closely spaced objects apart. Two factors control its size: the wavelength of light and the diameter of the mirror. Shorter wavelength means a smaller spot. Bigger mirror means a smaller spot. There's no other way to tweak it. It's like painting with a brush. A thin brush draws fine lines and tiny details. A thick brush just blends everything together. The wavelength is like the thickness of the bristles. The mirror's diameter is how hard you press that brush against the paper, shrinking the contact spot. But beyond a certain point, the stroke won't get any finer. Physics simply won't allow it. In astronomical images, stars appear as bright spots, but the size of these spots doesn't reflect the star's actual angular size. That's tiny. Instead, it depends on how bright the star is. The brighter the star, the more light spills into diffraction rings, spreading its halo across the detector. This light floods the surrounding area, overwhelming it like a spotlight shining on a lawn in front of a house. And if there's a coin lying somewhere on that lawn, it simply disappears into the glow. The coin is the planet. Let's return to Proxima Centauri, our closest star, just over 4 light-years away. It has a planet, Proxima Centauri b, a rocky world in the habitable zone. On paper, it's one of the best candidates for a second Earth, but in photographs, nothing. The planet hides inside the star's bright halo, not beside it or on the edge, right inside, submerged in a glowing mist like a pebble at the bottom of an illuminated fountain. Standard methods can't detect it directly. Here's the crucial point. This isn't a limitation of any specific telescope. It's not about budget or engineering daring. It's diffraction, the wave nature of light itself. It doesn't care how perfectly polished the mirror is. Diffraction affects a 2-meter mirror just as much as a 20-meter one. The only difference is scale. A bigger mirror means a smaller diffraction pattern, which improves the odds of pulling a planet out of the star's glare. But that pattern never disappears. Not ever. You could ask the question another way. If the star blurs into a bright spot and the planet gets lost inside that blur, why not just block out the star? Put up a shield to cut its light, leaving the planet shining against a clean, dark background. The idea sounds almost obvious, but between seeming obvious and actually working lies a chasm, where engineering runs headfirst into diffraction again, this time along the edges of the shield itself. A coronagraph works like this. It's a tiny opaque disk inside a telescope that blocks out the star, letting us see what hides in its glare. Think of it like shading your eyes with your hand to spot someone standing next to a bright street lamp. But instead of a hand, this disk is polished to nanometer precision. And instead of eyes, there's a sensor that counts individual photons. Coronagraphs are already in use, built into existing instruments. They've captured direct images of several exoplanets, though only young gas giants, heated to thousands of degrees, glowing fiercely with their own heat. Earth, next to its star, appears 10 billion times dimmer. A coronagraph helps, but it's no magician. Here, engineers came up with an idea that sounds almost crazy. What if we move the shutter outside the telescope? Not a disk inside the optical tube, but a separate spacecraft, a gigantic flower-like umbrella, tens of meters wide, that flies tens of thousands of kilometers ahead of the telescope, completely blocking the star. Two spacecraft drifting in the vast emptiness of space, yet working together as a single instrument. The star disappears behind the umbrella's petals, and the telescope only sees what remains around it, the planet. This technology of flying in formation is not science fiction. The Solar Orbiter Probe 3, launched by the European Space Agency, already puts this idea into practice. Two spacecraft fly in tight formation. One creates an artificial solar eclipse for the other, allowing it to observe the sun's corona. These two satellites maintain formation with millimeter precision, separated by 150 meters. Simply put, we already know how to make a pair of spacecraft operate as a single unit, separated only by the vast emptiness of space. Here's where it doesn't add up. A coronagraph blocks out the star. A starshade does an even better job. Suddenly, the planet appears against a clean, dark background. It seems like a win. But this victory only gives us a single point, a lone pixel of light. Bright? Yes. Separate from the star? Definitely. But still, just a pixel. No continents, no oceans, no atmosphere visible in the image. Because blocking the star is only half the battle. The other half is resolution, our ability to distinguish details on the planet's disk. And that's where the math starts to get unsettling. Hubble, a veteran of Earth's orbit with a mere 2.4 meters across. Its resolution is about 5/100ths of an arcsecond. To create even a rough map of an exoplanet, a 10 by 10 pixel grid, you need a resolution around 0.000085 arcseconds. Hubble falls short by almost 60,000 times. 60,000. That's like trying to read a car's license plate not just across the street, but from the other side of the country. Then there's James Webb. Its mirror measures 6.5 meters, nearly 3 times larger. But Webb operates in the infrared spectrum, around 2 micrometers wavelength, giving it a resolution of about 7/100ths of an arcsecond. In practice, that's roughly the same sharpness as Hubble. Bigger mirror, longer wavelength, resulting in nearly identical visual clarity. The LUVOIR project, seen as the next big leap, planned a 15-meter mirror in space. Its estimated resolution was about 9,000ths of an arcsecond. That sounds like a massive breakthrough compared to the Hubble Space Telescope, and it really was a breakthrough, but there's still a gap thousands of times too wide to reach the level we need. Eventually, they canceled the project and transformed it into a more modest next-generation observatory. This new design will be able to directly see Earth-like planets. Period. And what about here on Earth? The extremely large telescope, under construction in the Atacama Desert in Chile, features a 39-meter mirror, the largest optical instrument ever built by humanity. Its resolution is about 5/1000ths of an arcsecond, better than LUVOIR, the best we've ever created. Yet even this falls orders of magnitude short of what we need to map an alien world in detail. We can line up all these instruments, from the Hubble with its 2.5-meter mirror to the giant in the Atacama Desert boasting 39 meters. The mirrors grew larger. Budgets swelled. Technology advanced, generation after generation. Every new telescope stood as an engineering triumph, pushing the limits of what we could see. Yet none of them, whether orbiting in space, perched atop a mountain, or still on the drawing board, can capture a direct image of an exoplanet's surface. Not even a crude one. not even at 10 by 10 pixels. This isn't a matter of time. It's not about waiting for the next generation. For the past 400 years, astronomy has followed one path. Build bigger mirrors, polish them more precisely, lift them higher. But that path leads to a dead end. It will help us discover a planet, measure its mass, analyze its atmosphere through its spectrum. But revealing what it actually looks like? No. Classical optics hit a hard limit. You can't break through it just by adding more meters to the mirror's diameter. And if none of these instruments can give us a detailed map, it begs an uncomfortable question. Just how big would a mirror have to be to make this goal even remotely possible? Let's lower the bar to an absurd minimum. Not a map showing continents, not a photo with clouds, not even a blurry spot where you can make out day and night. The goal is a picture just 10 by 10 pixels, 100 points, smaller than the icon of an app on your phone screen. A planet the size of Earth, 10 parsecs away, that's about 32.5 light years. The nearest star systems where rocky worlds might actually exist. If we can't get even that, the conversation ends here. Any astronomical image depends on two key things. First, angular resolution. That's the ability to distinguish 2 points that lie close together in the sky. Second, photons. Enough light so each pixel doesn't drown in noise. Without the first, the image becomes a fuzzy blur. Without the second, it's a black square sprinkled with random static. You need both at once. And here's where the first trap appears. It might seem obvious. If there isn't enough light, just collect it longer. Leave the shutter open for an hour, a day, even a month. Astronomers do this all the time. The Hubble Space Telescope captured the same tiny patch of sky for 11 days straight to create the famous deep field. So why not do the same with an exoplanet? Here's why not. A planet isn't a fixed galaxy. It spins on its axis. Clouds form and dissipate. It orbits its star, constantly changing the angle of illumination. While the telescope patiently gathers photons over hours, the planet's surface shifts, morphing beyond recognition. It's like trying to photograph a person's face with a week-long exposure. They turn, blink, step out of frame. The result? A featureless blur. Long exposures simply don't work for a world in motion. That means we have to capture light quickly, in minutes, maybe hours, but not days or weeks. The only way to gather more photons in a short time is to increase the mirror's surface area. A bigger aperture acts like a wider funnel for light. A telescope with a 10-meter mirror collects 16 times more photons per second than one with a 2.5-meter mirror. Simply put, a larger mirror lets you shorten the exposure time. But a bigger mirror offers something else too. Increasing the aperture improves the angular resolution. Two critical factors, light gathering and sharpness, both depend on the same variable, diameter. So it all comes down to one question. How large does the diameter need to be? And that's where the real calculations begin. The diffraction limit formula connects three key factors: resolution, the wavelength of light, and the diameter of the mirror. Want to see finer details? You have two choices: observe at a shorter wavelength or build a bigger mirror. There's no third option. Physics doesn't negotiate. For ground-based telescopes, the challenge is even tougher. Earth's atmosphere shakes and stirs, blurring the image long before the instrument hits its diffraction limit. Adaptive optics offers a partial fix. Deformable mirrors adjust to distortions hundreds of times every second. But even the best adaptive optics can't reach the theoretical ideal. Space telescopes, freed from atmospheric interference, deliver clearer views. Still, they obey the same fundamental formula. So here's the goal: 10 pixels across the disk of an Earth-like planet located 10 parsecs away. What does that translate to in angular units? At that distance, Earth would appear about 8.5 micro-arcseconds wide in the sky. To break that angle into 10 pixels, each pixel needs to cover just 0.85 micro-arcseconds. Wait, what exactly is a micro-arcsecond? A second of arc is 1/3600th of a degree. A millisecond of arc is 1,000th of a second of arc. And a microsecond of arc is 1/millionth of a second of arc. The best telescopes we have today work at precisions measured in tens of milliseconds of arc. We need 0.85 microarcseconds. That's tens of thousands of times sharper. Plugging the numbers into the formula, with a wavelength of 550 nanometers, the green light in the middle of the visible spectrum, and a required resolution of 0.85 microarcseconds, we get a mirror diameter of 162 kilometers. Not meters, kilometers. For comparison, the largest optical telescope currently under construction, the massive giant in the Chilean desert, has a mirror 39 meters wide. 162 kilometers. That's 4,000 times larger. This isn't just a mirror, it's the size of a large asteroid. Place it on a map, and it would cover the area from New York City to Philadelphia. Or, if you prefer, from San Francisco to San Jose. A single, flawless mirror, polished to nanometer precision, floating in space. What if it doesn't have to be a single, massive telescope? What if we try interferometry instead? Imagine spreading several small telescopes across the right distance and combining their signals. That's how radio interferometers work here on Earth. It's how we captured the shadow of a black hole. But in radio waves, the wavelengths stretch millimeters long. Synchronizing those signals is relatively straightforward. Visible light, however, has wavelengths just a few hundred nanometers long. For an interferometer to work with visible light, its components must maintain their relative positions within fractions of a wavelength, over distances of tens of kilometers. Out in space, where there's no solid foundation and every tiny micronewton of solar wind pressure can shift the structure, nobody has yet figured out how to stabilize a formation of spacecraft with that kind of precision across such vast distances. This isn't a challenge for the next decade. It lies beyond any technology that exists today, not even on paper. This is what lies behind the modest goal of capturing a 100-pixel image. Remember that formula? Resolution depends on the wavelength and the diameter? It worked well for star clusters and distant galaxies, and it still applies here. The same relationship, the same two levers. But when it comes to exoplanets, both levers hit a wall. You can't go shorter than visible light wavelength without losing information, and building a mirror larger than 160 kilometers is simply impossible. Here's an intriguing detail. If we don't need an actual surface image, but only data about what's on that surface, like the atmospheric spectral composition or how brightness changes over time, the telescope requirements drop by orders of magnitude. A single flickering point of light can reveal surprisingly much about a planet, but that's a whole different approach. For now, the fact remains. Capturing a direct image of an exoplanet, even a rough one where the entire planet fits into a 10 by 10 pixel square, requires a mirror as large as a small European country. And no existing or planned technology is getting us any closer to building it. But what if we've been asking the wrong question all along? What if, to understand the surface of a distant world, we don't actually need a photograph? It sounds like a trick. Yet astrophysicists have reached this conclusion after hitting the limits of optics. No one is about to build a telescope mirror the size of Belgium. Still, the light reaching us from that distant planet, even if it's compressed into a single pinpoint, carries properties we can decode. Not as an image, as a code. The first method relies on eclipses. When a scorching hot exoplanet, a blazing gas giant, passes behind its star and disappears from view for a few hours, the system's overall brightness drops. But it doesn't dim evenly. The planet's infrared glow, its own heat, fades in stages, like someone pulling a curtain from left to right. The star's edge first blocks one hemisphere, then the other. By carefully recording how the infrared light changes every second during this eclipse, we can reconstruct a map of temperature across the planet's surface. Hotter areas cause the brightness to linger longer. Cooler spots fade away sooner. The Spitzer and James Webb telescopes have already used this technique on hot Jupiters, producing rough but real thermal maps of distant worlds. The second method is Doppler-based. The planet spins. One side moves toward us, the other moves away. Light from the approaching side shifts slightly toward the blue end of the spectrum, while light from the receding side shifts toward the red. If the surface is uniform, these shifts balance out perfectly. But if one hemisphere hosts a bright spot, a massive storm, a hot patch, a cloud band, that symmetry breaks. By analyzing how this imbalance unfolds, scientists can pinpoint exactly where the anomaly sits on the planet's disk. It's like listening to a rotating lighthouse with your eyes closed. By tracking how the horn's pitch changes, you figure out which way the beam is pointing. Using this technique, researchers have already mapped the surface of a brown dwarf, a celestial body that, even through the best telescope, looks like a featureless glowing dot. And here is where we should pause for a moment, because what comes next is truly the most elegant part. Both methods, the eclipse technique and the Doppler method, work with hot objects that emit their own light. But what about a cold, rocky planet that only reflects the light from its star? It doesn't have its own infrared signal to break down into hemispheres. All we get is reflected light, a faint, distant glow compressed into a single pixel. You might think there's nothing to glean from just a flickering dot, but here's the intriguing part. That dot doesn't flicker by chance. As a planet spins, different parts of its surface turn toward the observer. Oceans reflect light differently than continents. Ice caps shine unlike deserts. Clouds shift the planet's reflectivity every few hours. All these changes combine into a brightness curve, a graph that tracks light intensity over time. This curve carries a fingerprint of the planet's geography. Take Saturn's moon Iapetus, for example. It's famously two-faced, with one dark hemisphere and one bright. Its brightness curve shows a distinct asymmetry, revealing the sharp contrast between its hemispheres long before detailed images existed. The same goes for the dwarf planet Haumea. By analyzing its brightness variations, astronomers discovered it's elongated, like a rugby ball, and covered with patches of different materials. And all this insight comes from a single point of light. No shape, no size, just a flicker in the telescope's eyepiece. Simply put, a planet's surface leaves a signature in the rhythm of its shimmer. And if you know how to decode that signature, you can reconstruct a map. This is exactly what they tested in computer simulations. Researchers took Earth, our real Earth, with its oceans, the Sahara Desert, Antarctica, and Pacific clouds, and simulated how it would appear from tens of light years away. Just one pixel, a flickering dot of bluish light. Then they fed this brightness curve into an algorithm and asked it to reconstruct a map. The result was blurry and crude, lacking fine details, but unmistakable. The outlines of continents emerged, oceans separated from land. Earth reassembled itself from its own flicker, like an image forming out of static on an untuned screen. And then, there's one more leap. Other studies revealed something surprising. If you add just a handful of pixels from direct observation to the brightness curve, not 100, not 10, but literally 2 or 3, the quality of the reconstruction jumps. The algorithm gains reference points and starts to unravel the flicker with guidance, not blindly. Details come into focus. Edges sharpen. From almost nothing, something begins to take shape. The data we once dismissed as sparse, a single pixel, a flicker in brightness, a tremble in the spectrum, turned out not to be garbage, but raw material. We just needed the right mathematical tool to turn that shadow into a map. And that tool already exists. But to feed it truly high-quality data, some physicists looked at an object no one had ever seen as an optical instrument. An object weighing 330,000 times the mass of Earth, hanging right there in our cosmic backyard. The Sun. A blazing sphere of plasma nearly 1.5 million kilometers across, where every second 600 million tons of hydrogen fuse into helium. We usually think of it as a source of light and heat, but it has another feature, one that scientists only started considering in the last few decades when studying exoplanets. The Sun's mass, about 2 nonillion kilograms, a number with 30 zeros, warps the space-time around it. The fabric of the universe near the sun bends like a mattress under a heavy ball. Light passing by doesn't travel in a straight line. It curves around the sun, following the distortion in space. Photons from a distant star or planet passing on either side of our star converge at a single point behind it, just like a glass lens focuses beams of light. In simple terms, the sun acts like a gigantic magnifying glass. Only here, gravity replaces the glass, and the distant exoplanet's light, traveling across tens of light years, takes the place of the desk lamp. Einstein predicted this effect long ago. Here's the fascinating part. Place a telescope exactly at the focal point of this gravitational lens, and it won't just capture the amplified light from a distant world. Instead, it will see a ring. A thin, glowing ring encircling the dark disk of the sun, the Einstein ring. This is the exoplanet's image, stretched and smeared by gravity along a circle. It's warped, distorted, nothing like a clear photograph. Yet, this is where the real magic begins. It's mathematically reversible. An algorithm can take that ring and unfold it back into a flat map of the surface. Oceans, continents, cloud formations, everything we've struggled to extract from the flicker of a single pixel suddenly spreads out like the open pages of an atlas. And here comes a number that takes your breath away. Simulations show that the solar gravitational lens method could theoretically produce an image of an exoplanet with a resolution of 1024 by 1024 pixels. That's over 1 million pixels. Not just a blurry spot with vague outlines. This would be a full, detailed photo, comparable to an image of Earth taken from an airplane window. You could see weather fronts, coastlines, the color differences between forests and deserts. All of this from a planet tens of light years away. To put that in perspective, all previous methods we've discussed, light curve analysis, spectral studies, even direct observations with future telescopes, yield only a handful to a few dozen pixels. The sun's gravitational lens promises a jump of 3 orders of magnitude. It's like spending your whole life hearing a painting described on the radio, then suddenly being handed a ticket to the museum. But where exactly do you have to stand for this museum to open its doors? And here, all the excitement comes down to one number: 550 astronomical units. That's the minimum distance from the sun where photons from a distant planet can actually converge and focus. Any closer, and the lens simply won't work. Geometry just won't allow it. 550 astronomical units. Let's break that down. 1 astronomical unit is the distance from Earth to the sun, about 150 million kilometers. Multiply that by 550, and you get over 80 billion kilometers. That's beyond Neptune's orbit, beyond Pluto's orbit, even past the Kuiper belt. This is truly interstellar space. Imagine you're traveling there aboard a spacecraft. You launch from Earth and accelerate to the speed of Voyager 1, the fastest human-made object to ever leave our solar system. 17 kilometers per second. Voyager launched in 1977, almost 50 years of flight. In that time, it has traveled 163 astronomical units away from the sun. 163. But you need 550, more than 3 times farther. For Voyager to reach the focal point of the sun's gravitational lens, it would take over 100 more years, assuming it's even heading in the right direction. And it's not. Its path was shaped by the gravity of Jupiter and Saturn back in the late 70s. Here lies the cruel irony. The most powerful optical instrument in the entire solar system already exists. It's free. It needs no mirrors, no segments, no cooling to minus 270 degrees. It just hangs there at the center, waiting. But to use it, you have to travel so far away from it that no spacecraft in human history has ever even come close to that point. And notice, the telescope and its lens are separated. They're not a single device. The lens, the sun, stays put. The telescope must fly in the opposite direction, into the cold void beyond everything familiar, and there, in absolute solitude, catch the faint ring of light around a distant bright spot. two parts of one instrument spread 80 billion kilometers apart. Between them, nothing. No repair stations, no communication relays, no chance for a second try. Physics doesn't forbid this journey. The laws of nature don't put up a barrier. Gravitational lensing is real. We see its effects on distant galaxies, where light bends around clusters of dark matter. This principle works at every scale, from galaxy clusters down to a single star. The math checks out. Simulations reveal millions of pixels. An Einstein ring can unfold into a detailed map. The only thing missing is centuries of patience and an engine that doesn't yet exist. But if the sun can act as a lens, what's stopping us from looking closer to home? Maybe something beneath our very feet, just viewed from an entirely different angle. Astrophysicist David Kipping took a fresh approach. He didn't see Earth as a place, but as an optical element. Imagine a thin layer of gas wrapped around a rocky sphere. At about 8 miles above the surface, in the upper troposphere, the air is still dense enough to bend light, yet thin enough not to absorb it completely. A beam of light from a distant star, grazing the atmosphere at this altitude, bends slightly inward, just like a straw appears bent in a glass of water, but on a vastly larger scale. Earth becomes a glass nearly 8,000 miles wide. The refracted rays converge at a single point, not nearby, not in orbit, but roughly 1.5 million miles away, almost 4 times the distance to the moon. Right there, at that focal point, you could place a receiver, a normal telescope, a small one. Kipping called this setup the terrascope, a telescope that uses Earth's entire atmosphere as a lens. The numbers he came up with sound almost unreal. The atmospheric lens, in theory, boosts the incoming signal by 45,000 times. A 1-meter mirror, suspended 1.5 million miles from Earth, looks straight through our atmosphere and collects as much light as a traditional telescope with a 150-meter wide mirror. To put it simply, that's a mirror the size of 1.5 football fields, packed inside a tube you could wrap your hands around. No ground-based telescope in history has come anywhere close to a 150-meter aperture. The European Extremely Large Telescope, being built in Chile right now, stretches to 39 meters. And here, just 1 meter. With the atmosphere doing the rest. But here's the twist. The very atmosphere that provides this incredible lens also spoils it at the same time. Sunlight floods a thin layer of air with scattered rays. The atmosphere itself glows. Oxygen and nitrogen molecules re-radiate energy. Below, cities pump artificial light upward. All of this creates a noisy backdrop over the faint signal from a distant star. The terrascope only operates when the target lies on Earth's night side, far from the sun and away from city lights. And even then, the atmospheric glow doesn't disappear. The photons we need to capture get drowned out by countless unwanted photons. It's like trying to hear a whisper through a wall while a vacuum cleaner runs on the other side. The wall amplifies the sound, sure, but so does the vacuum. Here's the key takeaway everything leads up to. Even with its 45,000 times magnification, the terrascope in its basic setup can't capture a detailed direct photo of an exoplanet. Continents, oceans, even cloud cover all remain beyond its resolution. Yet, the terrascope is far more feasible than the solar gravitational lens. 1.5 million kilometers, that's not 550 astronomical units. It's a distance we already know how to send spacecraft to. The James Webb Space Telescope hangs out at that exact spot, Lagrange point L2. That creates a paradox. The lens we can reach is too weak. The lens powerful enough is out of reach. Now, take a step back, not from the telescope, from the whole story. Let's build a scale. The Hubble Space Telescope orbits low above Earth, about 540 kilometers from the surface. That's our first step. From there, it can see galaxies at the edge of the observable universe, but it can't resolve an Earth-sized exoplanet. To Hubble, such a planet simply doesn't exist as a distinct surface. The second step lies 1.5 million kilometers away. This is the terrascope. an atmospheric lens that boosts magnification by tens of thousands of times. Still, that's not enough for a direct image. The third step sits 550 astronomical units out. Here, the sun acts as a gravitational lens, allowing a 1,000,000-pixel map of a distant planet's disk. You can see continents on that map. But reaching that point means traveling more than 82 billion kilometers, a distance no human-made engine can cover within a human lifetime. 540 kilometers, 1.5 million, 82 billion, 3 points on a line. Humanity stands at the first one. We can't just snap a photo of an Earth twin. Traditional optics hit a wall with the laws of diffraction. No mirror, no matter how big, can deliver the resolution we need. This isn't a matter of engineering, it's a physical limit. But the universe, it turns out, left some loopholes. The atmosphere bends light. Gravity warps space. Stars and planets become lenses. You just have to be in the right spot. And each spot lies farther than the last. Reaching them means not just building new instruments, but advancing to a whole new level of civilization. Arthur C. Clarke once said, "Any sufficiently advanced technology is indistinguishable from magic." The trick of the solar gravitational lens, that's exactly that kind of magic. It's real. It exists. The math checks out. Now, the Einstein ring is waiting. We just need to grow into it. Somewhere, maybe 4 or 40 or even 400 light years away, a planet spins. Right now, someone there might be looking at their star, thinking the exact same thing we are. If they've advanced far enough on their own scale, they might already see us. A blue dot, clouds drifting over the Pacific Ocean, the sparkling lights of cities at night. But for now, we see only a single pixel, one warm pixel in a transit curve. Yet this isn't the end of our observations. It's just the beginning. We are a civilization that has just learned to squint. A lens made from our own atmosphere, a lens shaped by our parent star. We searched for a bigger mirror, but the universe whispered, "Look closely." Light glides along the edge of the troposphere, bending under the weight at the solar boundary. 80 billion times to focus, and finally, the face of an alien world emerges from the darkness. But for now, just one trembling pixel. Warm, moist, maybe alive. And behind it stands not a telescope, but faith. Faith that the journey is worth every moment of silence.